Well, it's wonderful to be here speaking with all of you today. As Lars said, I'm a theorist. I like to work on a lot of different things. That's one of the things that I really like about my job, thinking about planets. How you make a planet involves many different kinds of physics and a lot of history. A planet remembers where it came from. And so I can think about a lot of different things and claim that they're all the same and always be learning throughout my career. So I'm going to be talking to you today about how you make chemically diverse planets out of average galactic material. And I just want to say up front, the last time I took a chemistry class was in high school. But I've learned a lot of chemistry, and that's, again, one of the things I love about my job, is that I can always be learning new things. Okay, so planets. This is my favorite one. I don't want to live anywhere else because they're not as good. We just were learning from the polar climate group yesterday about how we're losing our Arctic ice at a rate that it may be gone in my daughter's lifetime, which makes me pretty sad. Yeah. So, yeah. Same one. All right. Perfect. I'd really like to, as an astronomer and a physicist, I really want to understand this planet in context. And there are a lot of different things I could mean by that. Right? I could mean, are there little green men out there? And honestly, I'd really like to know, but we're not there yet. But we're closer than we have ever been to looking for that. So that's really exciting. I'm a part of an astrobiology program at UC Santa Cruz, and it's turning into an actual discipline, which is very fun. I'm not going to talk about that today. I could mean, how do we make planetary systems like our own? And that's something that I spend a lot of my time thinking about, because physics will tell us how we make the structure of a planetary system, and that's the context that Earth lives inside of, and has really affected its history. But what I'm going to talk about today is how do we figure out what, just on a basic level, Earth is made of? You know, what's its bulk composition? You know, what's under our feet? Why did it get to be this way? And I'm going to start with the end of my talk, which is a result from the James Webb Space Telescope, which you probably know is flying now. It's this new facility that's bringing us fantastic new results. And as part of our program here on planet formation in the inner regions of planetary systems, and just for context, we're living in the inner region of our planetary system, so we're talking about right here. We have new spectra of young planet-forming disks. So this is a set of spectra from the JWST survey from the James Webb Space Telescope, and all of these different spectra look different, and by the end of this talk, I hope that you'll understand why we're both puzzled by and really excited by these, and why, as physicists, we feel like these are as gorgeous as any beautiful picture you can get from a telescope, because spectra are what put the physics in astrophysics. All right. Okay. So to get there, I'm going to go through a story here. And each of these pieces of the story I could spend a whole talk on. So feel free to ask me questions about any of them. I'm just going to go through a little bit of each one. We're going to talk about, what is under our feet, the solar system planet examples, what are the building blocks that we could be thinking about, interpreting the periodic table from an astrophysical perspective, the context of planetary assembly and formation, like I said, spectra physics and astrophysics. Now looking at those disks, it's more complicated than our original model, because isn't it always? And then we'll come back to where I started with these new insights from James Webb Space Telescope. All right, so the solar system planets. Here's a diagram of the structure of the solar system. The distances here are to scale. The sizes of the planets, of course, are not, because you can't put them on the same diagram and see them. They're all tiny dots. In the middle, we have our terrestrial planets, Mercury, Venus, Earth, Mars. Then we have our Jupiter and Saturn, gas giants, Uranus and Neptune. Separated by a couple of belts, and out here, Pluto, we didn't lose a planet, we gained a belt, and it learned so much about how our outer planets, moved around in the early lifetime of the solar system from it. So I'm glad we did, even though Pluto is wonderful. Here's, a picture of some of the planets with their sizes to scale. So Jupiter, Neptune, and then Earth and Mars. And so, just from this, we can see, of course, that they're very different from each other. The terrestrial planets, in addition to being a lot smaller, have very low fractions of their mass in their atmospheres. And Earth, it's 1/1,000,000th of our mass. You can see it on the little thin atmosphere here probably from the space shuttle. I don't actually remember where this picture comes from, but you can also see it in Mars. The ice giants are about 10% hydrogen and helium gas. And then when you get to the gas giants like Jupiter, these are more than 95% of the planet's mass is hydrogen and helium gas. So these things are qualitatively very different from each other. In fact, if you look at the Galilean satellites around Jupiter, they look like a little planetary system. And the biggest Galilean satellites, you can stick them next to Mars, and they're not qualitatively that different objects. Okay, so what are they made of? The bulk composition of Earth, I said, is mostly not gas. It doesn't have a lot of hydrogen and helium in it. The most abundant elements are these four: oxygen, iron, silicon, and magnesium. If you look at Jupiter, it's mostly hydrogen and helium, but it does have some heavy to astronomers elements. I'll show you a periodic table in a second. What I mean by heavy is not heavy to any chemist. What I want you to look at here is just this brown line. And what this is the amount of this heavy element that's listed on the bottom compared to what the sun has. So the sun is also mostly hydrogen and helium. It has all the other elements in it too. And I'll just comment that we have a couple of nice new data points on this plot from NASA's Juno mission to Jupiter, which has given us a better understanding of both the carbon and the oxygen composition of Jupiter's atmosphere. It's very cold, and so the oxygen forms water droplets, like we're used to, clouds in the atmosphere, and it gets low enough in the atmosphere that you can't see it very well. And so it's been very ill-constrained, and Juno's helped us figure that out. But the upshot I want you to take from this is just that, you can sort of multiply the sun's composition by 3, roughly, and that's what you get in Jupiter. So Jupiter is like the sun, it's hydrogen and helium, but it has a little more of the heavy elements. All right. Okay. So where did that come from? What are the building blocks? Interpreting the periodic table. Okay, so it's really very simple. Planets are made from things that there are a lot of. It's not that surprising, right? We start with, this is elemental abundances. Here's the mass number of the element, the abundance at the time that the solar system formed. You got your hydrogen and helium, Big Bang nucleosynthesis, made a little bit of stuff. Then, so mostly hydrogen and helium. Then universe, then the universe formed some stars, right? And they started nuclear burning in their interiors. And you can burn and get energy from it all the way up to iron. That's the highest mass number for which fusion gives you energy. Beyond that, you need to put in energy to get it. And so beyond iron, it's all a lot rarer. You need supernovae, right, to do that, or other really energetic events. So here's iron on the periodic table. I've only showed you the very top of the periodic table because even the heaviest things I'm talking about are, compared to the whole periodic table, quite light. And just as a point of reference, in case you've heard people talk about supernovae, they're often talking about how nickel powers the supernova light curves, and it's because it's just the one just past iron. Okay. So we've got things down to iron that are forming in the bellies of stars. So I can tell you all about that. The next most abundant after hydrogen and helium are carbon, nitrogen, and oxygen. So if you're looking in protoplanetary disks where things are forming, we're usually thinking about little molecules made out of hydrogen, carbon, nitrogen, and oxygen. So there's a lot of stuff there. So C, you have to go 1, 2, 3, 4 to the end of the periodic table. That means it can take 4 hydrogens. You make methane out of it. Nitrogen, you make ammonia. Oxygen, you make water out of it. You can also combine carbon and oxygen to make carbon dioxide, carbon monoxide, any of the little molecules that you can make of these. Those are what we call volatile, and I'm going to come back to that in just a second. And then if you just sort of take a line and go a little bit down on the diagram, you get the next 4 things you pick up are magnesium, iron, silicon, and neon. And bingo, that was what that was what the solid Earth was made of. Magnesium, silicon, iron, and oxygen. And the reason we get oxygen, yeah, sorry, go ahead.
When you're at scale of abundance, I mean,
yeah.
It says, it looks like number of atoms, but that doesn't seem right. It's mass or number of atoms or what?
This is in number of atoms where it's scaled so that the number of, compared to silicon, where silicon is 10 to the 6.
So it's the number of atoms divided by 10 to the 6.
It's the number of atoms per silicon atom per 10 to the 6 silicon atoms. Yeah. And that's just that's the scaling that solar system people use because like if you look at a solar system body, there usually isn't very much hydrogen in it unless you're looking at the sun. Because it's very easy to lose your hydrogen. Like Earth loses its hydrogen very easily. So silicon is something that is very abundant, but isn't lost very easily. So that's why they scale it to silicon. But really, it's the relative numbers.
It's not mass.
That's correct. So what I showed for the Earth Baltic abundance was in weight percent. So that was mass. This is in number, but still, yeah, that's right. So this is a number of atoms. But it's just the stuff that there's most of. So magnesium, silicon, iron, and then we also have a lot of oxygen in rocks in the Earth because you can take silicon, add a couple of oxygen onto it. SiO2 is quartz. Silicates that you add magnesium to are what rock is. That's where you use rock. Okay, so that's it. That's what we're looking at. But the other piece of physics that's really critical here for understanding, what ends up in a planet is what I mentioned before and what we were just talking about, the volatility of these atoms. And what that means is how hot do you have to get before your atom is in a gas instead of in a rock. So if we want to keep something on Earth, if it's a rock, it stays. But if it's very volatile, if it's easy to put it into a gas, then you can lose it off the top of your planet. And so here, the things that are highly volatile, meaning they can be in a gas at less than 700 Kelvin, so that's pretty hot already, is hydrogen, everything in red here. So hydrogen, helium, carbon, and nitrogen. Oxygen is in white because water is very volatile, and silicates, the rock, is very solid. And water's, and about half of the oxygen's in water, and about half of it's in, or in the volatiles, and half of it's in the rock, roughly. And then if you look at the things that we said were in the bulk Earth, the magnesium, the iron, and the silicon, those are the bluer colors, meaning you have to heat them. Why do I don't know why they're called refractory. All it means is that at room temperature, they're solid. Or you have to heat them up really, really hot. So one of the nice things about exoplanets is that you have to learn the terminology of a lot of different fields. And that's why I'm defining it here. Refractory just means you're solid. Volatile means you're gaseous. Okay, so that's what we got. You got most of your stuff, and some of it is easier to put in a gas, some of it's easier to put in solids. But some of it is more easier to put in a gas, and some of it's less easier to put in a gas. Even if you're one of these volatile molecules, like water can be solid. Just cool it down, gets cold, make ice, it's solid. Right? So if you're out where Uranus and Neptune are formed, they're called ice giants because they formed out of solid ice in the outer parts of disks. Okay, so I'm not going to talk about the noble gases anymore because they don't play nicely with others. They don't do a lot of chemistry. And I already mentioned this, about half of the oxygens in volatile gases, half is in silicates. And I'll just comment, because I'm going to come back to it later, that at least in the interstellar medium, where all of our material comes from, half of the carbon is actually in hydrocarbons, so like think soot. And the other half is in volatiles. But unlike silicates, we don't have a whole lot of soot in the Earth. You have to get heated up to 500 Kelvin. We're at about 300 here on Earth to put your soot into the gas. And it's still a mystery why we're not a soot ball. And it's a question, maybe in other planetary systems, the terrestrial planets are actually like balls of hydrocarbons. It could well be the case. All right. So that's the building blocks. Are there any questions about that before I move on? All right. So now we're going to talk about planet formation. So how do you make a planet, and how can we put these building blocks together? So planets are the dregs of star formation. They're sort of little leftover debris after you form a star. This is the Orion star-forming region. Each of these little insets here is a baby star with a disk of gas around it. They have a disk because the material that's falling in to make the star has some angular momentum. So it has a hard time falling directly onto the star, and it ends up orbiting around the star and makes a disk. And that's where we make our planets. And the last decade has really increased our understanding of what those protoplanetary disks, the locations where planets form, are like, and that's because of the Atacama Large Millimeter Array. We call it ALMA. It's in Chile, up at high altitude. It looks in the millimeter and submillimeter wavelengths and lets you take pictures of very cold material in disks around young stars. So I'm going to show you some more ALMA images later, but I have to show you some now because they're gorgeous. These are from the D-Sharp survey, and these are disks that are forming planets. You can see immediately that they have structure to them. They have a lot of rings, gaps. Some of them have like little bumps there. Some of them, if you squint, they have kind of spiral arms, look like spiral galaxies almost. And it's still not clear to us whether these gaps are the result of planet formation or they're the result of physical processes that help planets form. Clearly, these disks are going to make planets. We know from statistical studies of planet populations that at least half of the stars in the sky, and probably basically all of them, host planetary systems. So these guys are all going to make planets, ish, at least. But we don't know if they're there yet. It's actually very difficult to tell whether in each of these gaps there's a young planet forming, or whether these rings where you see the bright parts, that's dust, is concentrated, is sort of on its way to making a planet later. Yeah.
How long does it take to make a planet?
So the disks last a few million years.
How long?
A few million years. So not very long on the scale of the lifetime of the sun, which is 4.5 billion. That's the limit. They might actually form a lot earlier than that. We don't know.
What is the upper left-hand one with the little red dot?
That one, I believe, is a companion, but it's always possible it's a background object. Sometimes when you look at them, you've got a galaxy back there that's tricking you. But I think that one's a companion, yeah.
Why are they always disks rather than like a globe or something?
Great question. It's because, so you imagine, you start out with a big cloud of gas and dust, right? It's rotating. If you're in the direction of the rotation, you're in the car, you get pushed outward. So everybody who's in the plane of rotation gets pushed out and has a hard time falling onto the star. But on the top and the bottom, they fall, and they can't stop. That's why there's disks everywhere in astrophysics. That's why galaxies are disks. That's why you get disks around black holes. Yeah, it's a great question. Any other questions? Oh. Yeah, so I'll get to that later, but excellent question. These are about 100 times the separation between the Earth and the Sun. So remember I was saying that we're living now in the inner disk. These are much bigger. Our outermost planet, Neptune, is at 30 astronomical units, where an astronomical unit is the distance between the Earth and the Sun, so 30 times the Earth-Sun distance. These typically extend to about 3 times that. But there's a range, ranging from tens of AU to several hundred AU, astronomical units. All right, cool. So we're making some planets in these disks, presumably. This is just an artist's conception. This is how you want to think about it. You've got a star in the middle. You've got a disk around it. The star is lighting it up. The disk has gas in it. It has dust in it. We have to figure out how we're going to separate that all out into planets. And if we look at the solar system, the fundamental idea that's going to be most relevant to what we're talking about in this plot is that if you're close to the star, this is obviously not to scale, you have less material to work with. If you're farther from the star, there's just the area of the circle is bigger, you have more material to work with. It's a little more complicated than that, but that's essentially what's going on. And so you make small, rocky things in the middle, bigger rocky things on the outside, and I'll tell you how that leads to a giant planet in the first place. But how do you make them? Well, you start with dust, and I do really mean dust, like micron-sized dust, like you throw dust up in the air. And as it goes around the star, it collides with other dust, and it sticks. And then it collides with some more dust, and it sticks. And you have to grow by many, many orders of magnitude in mass to get from dust to a planet. There are several roadblocks along the way that are challenging to get past. You have to think about how those small solids interact with the gas, whether when they collide with each other they actually stick or whether they break each other apart. There are a lot of challenges to it, but they stick, they collide, they grow, and you make something that's solid. And if you're a puny thing like Earth, then you're done. But if you make something that's about 10 times the mass of Earth, which you can if you're farther from the star, you have more area. You also have ice to work with out here, so that helps too, because a lot of your water has settled out, and so you have more solids. Then you can have a planet that has such a deep gravitational potential well that it accretes its own mass in hydrogen and helium gas as an atmosphere. It just collects it in its gravitational well. And now it's twice as massive. And so now it's going to collect its own mass again in gas. And oops, it's twice as massive, and so it runs away. And it becomes a very large gaseous planet. So you expect to make gas planets farther out in their disks. And those gas planets can then grab some more solid material from their nearby neighborhood. And that's how you build up a planet. So these ones are made of just the solids, and these are made of the solids and the gas. But the solids and the gas come in different steps. Like, they don't all come in at once. So you don't expect the amount of solids and the amount of gas that you get to reflect necessarily the overall composition of the disk that they're made out of. Okay. So just to say a little more about that, what do we have to work with here? We're starting with our star formation region. And, we're getting some gas, we're getting some dust. If you're far from the star where it's cold, you can have some icy dust out there to work with. If you're close to the star, you don't have your ice anymore. You just have, more refractory things, to use the word that Lars used. And most of the molecules in all of this are actually inherited from the ISM, the interstellar medium, from all of this gas that was out here before you made your star. When you get really close to the forming star, it can get hot enough that you can start doing some chemistry. Once you put your gas in a planet, you can do some chemistry. But when you're in the disk, you don't do a lot of chemistry. You just have whatever you had in terms of the molecules, and they're either solid because they're ices, or they're gas because they're hot enough to be gas. And the different ices, water ice, carbon dioxide, carbon monoxide are the most common ones that we see in these disks, have different freezing temperatures. So water is solid, closest in, then you get carbon dioxide and carbon monoxide the farthest out. So depending on where you are in the disk, what you've got in your ices and your solids varies. Okay, and this led to an idea that Karin Oberg and Ted Bergen and I had back in 2011 about how the location that you make a planet in a disk is going to affect its composition. And I'm going to tell you in a minute how this isn't good enough, which isn't surprising. We knew that at the time. But this has been a big bestseller, especially among extrasolar planet observers, because what it means is that you can look at an atmosphere of a planet, figure out what it's made of, and try to track back where you made that planet in its disk. And I'll tell you why this is still great and why it's not good enough as I go along. Okay, so what is this plot? So here's a star this way. That means you're to the right, you're farther away from the star. It means you're colder. This is where water is frozen. This is where carbon dioxide freezes out. This is where carbon monoxide freezes out. So beyond this, everything that you've got is in the solids. There's also some extra oxygen in the silicates, in the rock. I told you there's extra carbon in hydrocarbons. But these are the main volatiles, so the ones that can be in the solids or in the gas. All right, so let's start on the outside, because that's where the material starts. It falls in from the cloud, when it's cold. And what I want you to see here is this is the carbon to oxygen ratio. So this is the ratio of carbon atoms to oxygen atoms. So once you put all this stuff in a planet, it's not necessarily going to be carbon dioxide and water anymore. You might have some chemistry and make it into methane, right, like the CH4. But you're still going to keep your carbon and oxygen atoms. So that's what we're tracking here. The dotted line is the ratio in the sun. And then the solid line up top is the ratio in our disk gas, and the dashed is in the solids in the disk. So remember, these are sort of these are the chocolate chips, and this is sort of the cookie batter, right? We've got our solids and our gas, and we're going to put it all together to make a planet. In the outside, all of these things are solid. It's very cold. Everybody's frozen out. You go in a little farther. Now suddenly our carbon monoxide, it can't keep it together anymore. It goes into the gas. And because the solar C to O ratio is less than 1, if we add 1 carbon per oxygen that we add to the gas, we're making the C to O ratio of our gas higher. So that's what happens. We have more C to O in the gas, lower in the solids. CO2 changes the exact numbers, but the qualitative idea is similar. And then we go into the water, where water goes into the gas, though, and now most of our volatile material has ended up in the gas, and what's left in the solids is just this oxygen, the silicates, and whatever is left in the hydrocarbons. And you can see right here that this predicts that Earth, right in here, we're in at 1 AU, should be a acidic ball because there's a ton of carbon there, which empirically is not the case. So we have to figure out where it went. Okay, so this is the idea, and then just to take it one step further, we're going to make a planet out of this stuff. So we have a solid core, we have that gas that we created on top, and we can extra accreted solids on top of it. So we're going to be some mixture of the solids and the gas, and whatever that mixture is will tell us what our carbon to oxygen ratio is. And the upshot that remains true, and I think is really promising for our future ability to use exoplanet compositions to understand sort of where they formed in their disks and the structure of planetary systems formation and disk connect us all, is that the CDO ratio should not match that of the star. So that's the upshot. But of course, this is a simplified model. There are a lot of other things that can go on in the disk, and I'm going to tell you about some of that as I move on. Just in case you were wondering, extrasolar planets have a broad range of solid to gas ratios, right? So how much chocolate chip do you have compared to cookie batter? This is the ratio of chocolate chips to cookie batter compared to the star, and we can see in the sample of exoplanets that it does depend on the planet's mass, but there's a whole range across different planetary systems. So if we're putting these mixtures together, we don't expect them to come up with the same thing everywhere we look. All right. Okay, so that's my planet formation primer. And now we have to move on to spectra, which put the physics in astrophysics. Okay, here's the spectrum of the sun. This is going to feel like a digression for a moment, but then we'll come back to where we were before. Okay, spectrum of the sun. It's gorgeous. It's a rainbow. I love it. Okay, so up on the red side, those are the lower energy photons. They're, going like this. Higher energy photons going like this on the blue end. It's easy to remember because the blue is close to the ultraviolet. They're energetic. They burn your skin. The red, if you go farther up, you get to the infrared. If you wear infrared glasses, you can see us glow. We are not as energetic as the sun. Therefore, we are glowing more in the red with the lower energy photons. Okay. Notice that when you look at this, in addition to having these beautiful colors, it's dimmer over here, and brighter in here. That's because this is where the sun emits most of its light. That would be the peak of what we can see is not a coincidence. That's not physics, it's evolution, right? We evolved so that we use the light that's available to us, that the sun emits. And if I were putting this on a spectrum instead of this nice image, we would see it was, dimmer, and then it would go up, it was brighter, and then dimmer. So our spectrum would kind of look like that. And then we have dark spectral lines in here, and that's quantum mechanics. Right? So quantum mechanics says that if you have an atom and you want to take its electron has some angular momentum going around the proton. I know it's not actually doing that. It's a cloud. I'm going to pretend. I like to do the classical approximation. For me, it's good enough. Okay. You want to move it to a higher energy level. It has to jump in angular momentum. The Planck constant tells you, how much of a jump it has to make. Why does quantum mechanics do that? I don't know. Ask a particle physicist. But these lines here are all these electron transitions for atoms in the sun. Molecules do a similar thing, but molecules, you have your water, your H2O, or let's think about carbon monoxide because it just has two. They can also just rotate around each other, or they can vibrate back and forth. And they too are limited by the same Planck constant of angular momentum. But if you're more massive, now instead of being an electron, you're a nucleus of an atom, then you have, at the same velocity, you have more momentum, right? You have a big truck, it has a lower speed limit going downhill because it's hard to make them stop. And so the amount of energy difference between those angular momentum states is actually less, typically, for a molecule. And it's just because, the things that are rotating are more massive. And so if you want to look for lines that come from molecules rather than atoms, you got to look in the infrared. And that's where the James Webb Space Telescope is looking. And that's where many molecular lines are. And that's why it's so exciting that we have an infrared space telescope in space for looking at protoplanetary disks and planetary atmospheres. Because we can see, using quantum mechanics, what molecules are present. And I said, I don't know why, quantum mechanics is the thing, but it's really fortunate it is for us as astrophysicists, because it means that we can just use light to identify the compositions of things that we're looking at, and relate them to the atoms and molecules we're familiar with on Earth. So it's really useful. Okay. So we can do this both with wide separation giant planets that have been directly imaged. This one is the best because there are 4 planets and we can actually see them orbiting their star. It's a lot of fun. Most of the planets that we know we can't actually take pictures of like this. They're much closer to their stars, and we see them as they pass in front of their stars, and we can get a spectrum by looking at how much light from the star they block. But this one is a great system. Here's a spectrum from this system. I'm going to move past this pretty quickly. I just want to show you that it exists. But you see some, big dips in the spectrum in the infrared. And one thing that you'll notice here is instead of being a thin line, like we were looking at in the sun, there's sort of like big dips. And that's because molecules can rotate in a lot of different ways. They can vibrate in a lot of different ways. So they make a whole set of lines. And when we can't separate them all out individually, it looks like just like a big band. We call it a band. of absorption over a wide range of the spectrum. I'm going to skip past this and show you a different planet at the risk of being a little bit confusing because this one's upside down, but I'm showing it to you because it's the James Webb spectrum, and look, it actually looks like a spectrum. It's so exciting. Woo! It's not just a mess of dots. And this is amount of light blocked. So here, when you have a molecule, it goes up instead of going down. And this is a hot Jupiter that's located right close to its star. And you can see water absorption bands, carbon dioxide absorption bands, carbon dioxide again. Why are these the ones? It's because these are the small molecules that you can make out of the things that there are a lot of in the universe, like we talked about. All right, cool. So you can look at these planetary atmospheres. You can start figuring out what the planet's atmosphere is made of, and we can try to relate that back to where they formed. We don't think these planets formed very close to their stars, by the way. We think that they formed farther away and moved around. So it's all a big puzzle to put together. And we can try to relate those compositions to their formation. Okay, so let's go back to the disks where we're forming these out of. Right, here are a couple of pictures of a protoplanetary disk, and these are pictures of the dust in this disk. These are actually the same disk. This one's observed in the infrared, but not in one of those molecular lines. What we're seeing is light scattering off of the surface layer of the surface of dust in the disk. You can kind of see there's a dark lane here where you can't see anything because it's too absorbed by the dust. And it's sort of like, it looks like a bowl. And here, we're looking with ALMA in the millimeter. This is emission from bigger dust in the midplane, like the middle of the disk. And this is presumably closer to where the planets are forming. So even if we're not taking a full spectrum, we're taking images at different wavelengths to get at the different components of these disks that we're looking at, and putting together a physical picture based on this. And just related to what Lars was asking before, this is 10 AU, 10 times the distance between the Earth and the Sun. So this is a gigantic thing. We're like right there in the middle of it. Here's some more infrared scattered light images of disks. Like they have all these, so here you see a lot of them where you see that bowl on the top and these midplanes. You see some spiral arms like spiral galaxies. You see these like weird little gaps here, which we think are inner parts of the disk casting shadows on the outer parts. A lot of fun stuff here. We have, I already showed you this before, ALMA sort of millimeter, submillimeter images looking at glowing dust, cold glowing dust in the midplane of the disks. But we also have from ALMA some direct measurements of gas composition in these objects. So this is from the MAPS program, which is using ALMA to look for molecules in different disks. And the reason we can look for molecules is, remember, that they have those very specific wavelengths that they want to emit and absorb at quantum mechanically. And so we can just specifically look at those wavelengths, only those, and we know we're looking at the molecule. This is hydrogen cyanide in several disks from the program. But I think it's even more fun to look at the bottom one, 5 molecular faces of one disk. This is all the same disk. In carbon dioxide, hydrogen cyanide, C2H, I forget what you call that, but these are hydrocarbons here. And you can see that the same disk looks really different in all of these different molecules. And that's because the molecules are, sometimes they're in the gas, sometimes they're in the solids, sometimes they're chemically interacting with one of the major components of the disk in the gas or in the solids. So we can really start to put together what's going on in these disks, what are they made of. And just to tie this back to the dust, here's a set of disks looking at their carbon monoxide gas and the dust that's forming planets in the midplane. And you can see they don't look the same in those either. So here's to come back to my analogy, the chocolate chips, and here's the cookie dough. And we're going to try to put it all together to make some planets. All right. Okay. So we have this model. Now we can look at it with the data. So we're done, right? Of course not. All right. So of course it's more complicated than our original model. And now this has led to a flourishing of a lot of different processes physical processes that we can study going on in these disks. And I'll just show a few of them. So this was the original model I'm talking about. It's more complicated than this. Okay, here's one. If you look at the same disk at different wavelengths, which probe different particle sizes, it changes size. So the bigger particles are closer to the star, that's on this side, and the smaller particles in the gas are farther from the star. Why does that happen? Well, you have a disk. This is star over here. Here's your gas. You're made some rocks. You have some material that can form ice out here. It makes what we call pebbles. People call them pebbles. Really, they're kind of dust bunnies, but the field calls them pebbles, so oh well. Okay, so you make some dust bunnies, and they settle down to the midplane, and they start drifting through the gas toward the star. Why does that happen? Well, the disk actually is made of gas, and sort of it's pushing itself outward away from the star. So if we have a pebble in here, it wants to orbit the star at whatever speed it wants to orbit the star. But the gas that it's nearby thinks it's orbiting a slightly less massive star because the gas is pushing out on it. So it wants to go a little slower. And when this pebble is really small, gas drag makes it go at the gas velocity. So it has some extra pull from the star that it wouldn't otherwise have, and it'll start drifting in. And it'll fall toward the star at their terminal velocity. So just like, you drop your penny off the roof and it ends up at its terminal velocity. If you drop a heavier thing, the terminal velocity is faster. Drop a lighter thing, it's slower. Given the same, physical size. And so the bigger ones just drift toward the star faster. And so you end up with the larger particles drifting in more quickly, they end up closer to the star. So we know that we're making these pebbles, really dust bunnies, and they're drifting in toward the star, and they're carrying solid material with them. And if they get close enough to the star that they pass where the ice that they're carrying doesn't want to be solid anymore, then they desorb, they break up and put that material back into the gas. And so now you can actually move your material from the outer disk to the inner disk. And this is happening, sometimes some of this gas is also moving in toward the star, but much slower than this. So you can take some of your water that's out here, put it into ice, send it drifting into the star and release it over here. And you can move your components of your disk around in the nebula while you're making your planets. I don't want to go into the details of this, but I'll just say that we can actually see CO gas depletion in disks. What you're seeing here is, the dashed line is what it would be without putting the CO ice on the pebbles and drifting it. And the measurements are the solid lines, and we can make models that use this process to match the depletion that we're seeing. So we can be probing this process. And this is really an aside, but you might wonder, well, will a planet actually grow from these little dust bunnies? And it will. The planet will come in, it'll feel gas drag, and it'll actually help it get caught into the gravitational potential well of a planet and grow quickly. And here's a numerical simulation of this happening. So you can, so this has been a big change in our understanding of planet formation in the last decade, I would say, is including pebble accretion, like this really fast, direct growth based on these small solids that we can actually see directly are there, and they're drifting in toward their star. All right. Okay. So that gets me back to the beginning/end of my talk, which is, what are we doing here, and why are we so excited about this with these new insights from JWST? So I showed you all these pictures of the outer disk, and they're so far away from their stars compared to where we are living right here. So what's going on in the inner disk? So that's what we're spending our time here at KITP thinking about. How do planets form in the inner regions of protoplanetary disks? And there have been a lot of really fun results that people have presented. And I'm just telling you about just one of them, which are these new spectra from JWST. And these probe the inner disk, near where Earth formed. And I want you to notice, here, we'll focus on the top two here. So there's a diversity of them, first of all. They're not all the same, so we have to understand how different systems can make different things. But, look at all these lines. Instead of those nonsense bands, we've got actually lines from water molecules. And these are from hot water. So they're coming from close to the star. So we can take this spectrum, and we're seeing water that's in the gas close to the star. But if you look at the second one, oops, it's not all water. Look at this, C2H2 hydrogen cyanide. Okay, each of these is a water line. Okay, let's zoom in on one of these. These are hydrocarbons. Those are that soot I was talking about, right? So some of these, you can see the soot. We were wondering, where did all of that carbon go? In the gas near their stars. Here's an idea about what we're looking at. But I'm not going to say this is actually what's going on, because the whole point is I'm telling you about new data that we're all having a lot of fun trying to decipher while we're here. And that is, just like I was talking about before, you're making these pebble dust bunnies. They're being transported in the disk. They pass their, in this case, water snow line. They lose their water into the gas, and then eventually it ends up on the star. But now if we zoom in on this inner region, what's happening is that the pebbles are coming in. They're letting out their water gas. It's going up high in the disk. Let me stop for a second. Why does it have to go up high in the disk? It's because there's still a bunch of dust there, and the dust blocks our view of the water gas in the midplane. We can only see what's up at the top. And it gets up high enough. It has a little while, like 100 years, before the UV light from the star breaks it apart. And that's what we see. We're seeing the hot water that's hanging out at the top, or the hot hydrocarbons. And so one of the ideas that's been proposed is that as you transport your pebbles, first you transport your water, then as you wait long enough, you start transporting them in from those farther away reservoirs of carbon-rich solid material in the outer disk. And so, later on in the lifetime of the system, instead of seeing water gas, you'll see hydrocarbons as they drift in, and that's the gas that's desorbing. I'm not sure why you wouldn't also be bringing water at that later time, so that's one of the questions people have. But here I'll just show you one exciting correlation that we're trying to think about. So this is stellar mass and accretion rate. I haven't really talked about this much. This is how quickly the gas is falling onto the star. Because remember, what the whole point of this disk was to get the last dregs of the gas onto the star. Here are some measurements for a set of disks. This color bar tells you how many hydrocarbons do you have compared to water. So if you're orange up here, you got a lot of hydrocarbons. And if you're down at, purple, you have a lot of water. And if you look at this, it kind of looks like, well, the lower mass stars and the lower accretion rate ones have more hydrocarbons, and the higher mass stars, the ones that are accreting faster, have more water. So this could, in principle, point us in a different direction. Instead of thinking about the time evolution of the disk, there might be something about how aggressively your gas is moving onto the star that tells you, whether you're pulling in hydrocarbon gas or water. I don't know the answer. This is what we're excited about. I'm excited about trying to figure it out. Okay, so that's it. I started asking by saying, I was going to tell you how you can make chemically diverse planets out of average galactic material. I've told you some processes that can help us do that. But what the new JWST data has the potential to show us is how chemically diverse can planets made out of average galactic material be? Should we be looking around other stars for planets that look like Earth, but they're really hydrocarbon soot balls? And that just makes me think about what kind of life might form or not on planets like that. So thank you very much.
You're talking about chemically diverse planets, and so I'm reading a geology thing, and he's saying that Earth is one of the most chemically diverse planets because of light.
Right. So I'm using the word in a different way. I'm thinking about different planets being chemically, at a really basic level, fundamentally different from each other. But I would argue that we don't know yet whether, soot-ball planets could be as chemically diverse as Earth through the formation of life or other, interesting chemistry.
We don't really have the instrumentation to discover how chemically diverse planets and other solar systems would really be.
We don't, but I can say that, again, we're carbon-based life, but Earth is extremely carbon poor. The environment that life formed in here, the chemical environment, really must have impacted its evolution. So if we do find signatures, and I didn't have a chance to talk too much about that, of life on planets that have a different bulk composition to Earth, there's no reason to believe that it would be at all similar to life here. So I don't have an answer to your question. I think that we're at a really exciting moment where, I've been in this field for, 25 years, and we've learned dramatically a lot over that time period. When I was in high school was when we first discovered the first extrasolar planet. So I'm going on, but I think that we're going to be able to answer your question in my lifetime.
Yes, maybe this complicates things, but when does the formation of moons, which we have plenty of in our solar, when does that come into your picture?
Yeah, so for Earth, the Earth-Moon system, we have a pretty good constraint on that. We think it was formed in a major impact with a Mars-sized body, and that happened a little bit after the gas disk dissipated. So it's not during this sort of time where you have one of these disks we were looking at, but at the end of that time, you can have a bunch of sort of terrestrial bodies, and they can still collide with each other because they haven't quite finished their dynamical evolution. And I'm forgetting the exact age, of something like 40 million years after the beginning of the solar system. So a little longer than the disk lifetime. In general, though, while there are people who have been looking really hard for moons around extrasolar planets, they haven't found any yet, and it's not that surprising because most of the planets that we've found are actually very close to their star. And if you're close to your star, then tides from the star can pull a moon out of orbit much more easily. So I think that once we're able to find a lot more planets, that are farther away from their stars, we're going to expect to find more moons around them.
So how does the moon form? I mean, how do these moons form around the Jupiter or Saturn?
Oh, good question. So Jupiter's moons, Jupiter has two kinds of moons. It has the Galilean satellites, and we think that those formed in a disk around Jupiter, much like the disk that we were looking at, through very similar processes to the planet formation process that we were talking about. So you make a Jupiter, it's in a gas disk, but it actually accretes its own disk around it. But then it also has a whole bunch of other little moons that it dynamically captured, just as they were moving by. Yeah.
I hadn't heard about the soot-based planets before. Is the texture going to be, we're rocky here. Is this going to be a squishy?
I have no idea, and I have to give credit to Ted Bergen, who is another person who's been at our conference for promoting the soot planets. But he's right. I have no idea what they would be like. It's a good question, but they would have a lot of carbon in them. That's all I can say.
So
Yeah.
I have a question.
Yeah.
I understand the Earth is cooling.
Yes.
Is there any way we can prevent the cooling?
Cooling, like from its, so do you mean from the interior or do you mean from the interior? I can't think of a way we could prevent the cooling. I mean, it's coming out of volcanoes. It's a natural process. Yeah.
So the gaseous nature of our solar system is done, essentially.
That's right. It was only the first few million years, and now we're 4.5 billion years later.
So our gas planets, though, is their diameter relatively fixed, or are they either shrinking and or expanding?
Great question. So they're shrinking a little bit, and actually, if you look at the light coming from Jupiter, about half of it is reflected, reprocessed light that it's getting from the sun, energy, and the other half of the energy coming out of Jupiter is from its gravitational contraction, and it's just emitting that as light. When you look at young planets like those HR 8799 ones that I showed you that system orbiting, it's most of the light that's coming out is actually energy that comes from their contraction. It's not energy that comes from the star. So when you see a direct image of a planet, it's almost certainly at this point a young planet because those are the brightest ones. They're the hottest.
Our solar system is relatively stable at this point.
Yeah.
Is there like an obvious eventuality of another solar system kind of colliding with us? Is that out there?
It's possible. It's much more common to collide with another planetary system when you're young because stars form nearby each other. So we think that planetary systems are actually frequently shaped by other stars coming by in their youth. It's much less likely now. But when you think about the dynamics of planets, they always evolve over however old your system is. So wait another 4 billion years. The next one to go is probably Mercury. We'll probably hit the sun.